So anyhow, everybody, I'm so happy to see everyone and Happy New Year. I hope everybody is staying healthy and well. So I'm just absolutely delighted that we're going to start our spring seminar by talking about the exciting news, which is JWST. And we have Torsten Boker from Space Telescope Science Institute. He's an ESA scientist working there. And his functional work is, he's the calibration scientist. I think that's your title officially. It's Space Telescope, working on NIRSpec. And he also has a lot of programs with NIRSpec and MIRI science programs. And he's been working on nuclear star clusters and black holes and many more things. So I want to just begin by having Torsten give us an update and also thanking Torsten for all the amazing work and the entire JWST team for making this possible and having all of the persistence and enthusiasm as a community. We're very grateful. So Torsten, I want to hand it over to you, and I'm happy to share screen.
Well, wait a second. First of all, thanks a lot for having me, and of course I accept the thank you, because this was clearly a one-person effort. I did all this by myself, you know. But it is truly has been a blast. I mean, the last couple of weeks in 2021 and the first few in 2022 have been probably the most amazing ones of my career, because we've been waiting for so long, and then to have the launch go down so picture perfect. Everything was just like they drew it up, and I really couldn't believe it. And then the deployment started, and you know, of course we were biting our fingers and fearing for any moment that something might go wrong, but nothing went wrong. Everything went just perfectly. There were a couple of hiccups where they were scratching their heads for a day or two with the solar panels. The power calibration wasn't quite perfect, so they had a little bit too much juice on parts of the array and not enough juice on other parts of the array, so they had to recalibrate those. That cost us a day, but that all went well as too, and we're super happy with the performance. Right now, things have been slowing down a lot, because now that the major deployments are behind us, they have to move all the individual mirror segments out of their launch lock positions. And that is literally happening at the same speed that grass grows. They're moving them about 1 millimeter a day. And so for the past week and a bit, we've been just watching that happening. But it's okay, because there really isn't much else to do at this point in time. We're cruising towards L2. We're cooling down, so they can take all the time they need to do this right. And of course, the reason they're doing it so slowly is because these motors that they use are the same motors that are used for the fine adjustments. So they have nanometer resolutions. And if you have a nanometer resolution motor that needs to move things by centimeter, it just takes time. So there's a lot of revolutions that are needed there. So, and these are all mechanical gear motors. So you can imagine that it has to be happening slowly, because you also don't want things to heat up too much. So that's the reason why it takes so long. But yeah, everything is looking great. We are starting to power on the instruments for NIRSpec. It's going to happen in a couple of days that we turn on our other 2 electronics boxes. The micro shutter array has been powered on already, pretty much right after launch, because we had to control the temperatures of the array, of the quadrants, and that is progressing nicely as well. So yeah, keep your fingers crossed that we don't run into any major hiccups, but we'll soon have some light on the detectors. Messy, funky PSF, of course, because nothing is aligned yet, but at least we'll have a telescope in space, and that's already a great achievement for everybody. And yeah, I just wanted, in case you don't know, there's this website, Where is Web? I'm sure most, if not all of you, are well aware of it, where you can see daily updates of what is happening. Shobita is sharing her screen right now. If you scroll up a little bit, you can see where we are with respect to L2, what the current speed is, and so on and so on. And that really is a nice summary of the status. And you can see here, if you scroll down a bit, where the mirror segments are. In fact, 16 of the 18 are now fully deployed. The last 2 are being moved right now. So they're on their way to their nominal positions where they can start wiggling them around so they can start putting the PSF together. All of this is happening right now. And there's a lot of links there for the blog entries and different things. As I said, I'm sure most of you are aware of it. Yeah, that's really all I wanted to say. And thanks for letting me share the excitement. It's crazy times for sure.
Let's thank Torsten. So yeah, thank you so much, Torsten, for giving us that update and starting off our semester with enthusiasm.
Happy to take some questions if anybody wants to know something I missed saying. But of course, as I said, I can't share, even if there was something hot off the topic, I couldn't share that with the public unless it's published on that website or in the blog. That we have strict directives to not share confidential information, obviously. Don't want to get it out, but trust me when I say there really is nothing to report other than what I just said. Everything is indeed going very, very smoothly.
So we have a lot of people with JWST programs in this audience, so I don't know if anyone wants to ask specific questions on,
I've got one.
Jim, yeah.
What is the final unfurling step? What's the very last step when you'll say that the whole satellite is completely unfurled and ready to go?
I think as far as deployments go, we are already past that point. There is nothing major that needs to move into place other than the mirror segments. And as I said, 16 of the 18 are already there. So tomorrow, I think we'll be done with that. Then the next mechanical hurdle is the alignment of that telescope. And that will take another few weeks because of the complicated algorithms that are used to align all these all the 18 segments and bring the telescope into focus. But in terms of major movements of mechanisms, there's nothing left. It's all done.
Wow. David Rosario, did you have a question?
I did, but I've forgotten it. I'll come to it later.
Okay.
So one thing I should say that the event that marks the formal end of the travel or road to L2 is the orbit insertion, and that is happening on day 29, so around the 24th or 25th of January, when we will do another burn to put us into that halo orbit around the second Lagrange point, and that marks the end of the trip. And from then on, it's basically science operations mostly to align the telescope for the next couple of months, I think.
David might have remembered his question.
Yes, I remember my question. So I've heard Torsten, I've heard a couple of statements about potential lifetimes now that most of the deployment is done. Are there any critical steps for the before one can make a statement about that, or is it really just going to depend so much on the planned observations for the next several years before one can make a prediction?
That's certainly an aspect is the amount of slews that we need, and also how much momentum we have to burn off, and that depends on the observation program as well. But I think it's fair to say you won't get a concrete number because of all those vagaries, but for sure we have far exceed the 10-year lifetime. I think it's probably safe to assume that we have at least 15, maybe 20 years, and then how far we can stretch that depends on the details of the observation plan. But it's for sure that life propellant is not a limiting life factor at least for the first 10 years. Probably way more than that.
Great.
Oh,
Yeah.
that's wonderful news.
No, it really is. Ariane Spass did a great job with the launch.
Yeah. now I'm over the moon excited and grateful for the entire team. So thank you.
Just like your dog, right?
Yeah, you can see how excited he is. So anyhow, so thank you so much, Thorsten. And
No problem.
we're already a little bit past 10 minutes past the hour. So Mitchell, I think, can get started. And I'm absolutely delighted to introduce Mitchell to you. So yeah, I can share his screen. And Mitchell is an expert in AGN outflows and feedback in nearby galaxies. And this is a hot topic for JWST science. So many of you are very interested in that. So Mitchell got his bachelor's degree in physics from the College of New Jersey. And then he went on to get his PhD in astronomy under the guidance of Mike Crenshaw. I think he's also here, who's joined at Georgia State University, where he was awarded an NSF GRFP fellowship for his work on AGN outflows. And he's now a postdoc working at Space Telescope Science Institute, where he's focusing on ultra-deep studies of quasars, sightlines using HST and MUSE, and he's also continuing his AGN outflow work. And so in addition to his very active research career, Mitchell also does a lot of public outreach, and he serves on the AAS Employment Committee. So he's very passionate about early career scientists and finding their resources they need to succeed. So definitely contact Mitchell if you're an early career scientist and want some advice. So so he also is really looking to collaborate with people, and so people should reach out after this talk. And I should say that we will have our usual Discord session after the talk, and Jeffrey will put a link in the chat at the end where you can speak more with Mitchell after today's talk. So with that, I want to turn it over to Mitchell.
Thank you so much. Please at any point, just interrupt me if you can't hear me, or if anything is wrong with the slides, you can't see them, just go ahead and flag me down. Otherwise, thank you so much for that kind introduction, and welcome everyone to the first AGN seminar of 2022. As mentioned, I'm currently a postdoc at Space Telescope Science Institute, and today I'm really excited to kind of give you an overview of a summary of our investigations into the properties of mass outflows in nearby active galaxies. To begin, I'd like to go ahead and thank all my collaborators, including my supervisor, Mark Revalski, as well as my PhD advisor, Mike Crenshaw, who is one of the main drivers behind many of the studies I'll discuss today. So in this seminar series, we've had a lot of really excellent AGN presentations, and kind of a fundamental link is that we all share a common interest in the connections between supermassive black holes, their galaxies, and how they interact with the environments that they live in. So for this group, we require very little introduction to that topic, but just to give a very brief, concise background to kind of motivate the study, if things will advance. There we are. We now have substantial evidence that the majority of galaxies host a supermassive black hole at their center. And this black hole grows by accreting gas from its galaxy in a surrounding accretion disk. And this process releases an immense amount of radiation back into the galaxy, which can couple with the interstellar medium and drive these powerful mass outflows. So this process is kind of overall known as AGN feeding and feedback, and it appears in basically two main forms. The first are these mass outflows, kind of these wider angle outflows that we see in ionized and neutral and molecular gas, as well as radio jets, which are these very narrow pencil beam, more relativistic types of outflows that are very powerful in some types of galaxies. Now, I think a key that we've really started to get a picture of in this seminar series is that these outflows are important on basically all scales. So we might be interested in their impact for a variety of reasons. At some of the smaller scales, we have these correlations between the mass of the supermassive black hole and the large scale properties of the galaxy, such as the mass of the bulge. And currently, they're on such different spatial and gravitational scales, they're not really necessarily interacting. And so this is one piece of evidence that these systems kind of grew up together to establish these correlations. And of course, if we're also heating up and moving around a lot of material, that has the potential to impact the way stars form as we move out into the extremities of the galaxy. And in some of the larger systems, particularly those with radio jets, we're able to keep gas really hot. In the most extreme cases, we can heat gas within clusters and actually keep it hot and prevent it from cycling through galaxies, which is going to have implications for the cosmic baryon cycle. And kind of all of this ties into the formation of large-scale structure. Without this AGN feedback process, simulations basically don't match the size and luminosity distribution of galaxies that we see today. So this kind of overall picture hangs together nicely. You know, why haven't we figured this all out yet? And of course, it's because this is very difficult. These outflows are multi-phase and multi-scale. So very close to the supermassive black hole, we have these highly ionized, ultra-fast outflows. As we move out, we have ionized and neutral or molecular outflows, these radio jets. So there's a lot of pieces that require different observational data sets to probe. So for our studies, we've been particularly focused on narrow line region outflows. And so this is ionized gas that displays very strong emission lines, particularly in the optical as well as the UV and the infrared. And one of the reasons we're so interested in it is that it spans a very large dynamic range in spatial scales. So from basically less than a parsec from the supermassive black hole in some cases out to the kiloparsec scale post-galaxy environment where we might be impacting the formation of stars in the bulge, for example. So with this picture, we need a sample of targets to look at. And so the question is, where do we look for these outflows? So very, very close to us, AGN either tend to be too weak or there's not enough of them to get a good sample. And if we look further away at very luminous quasars, they tend to have very powerful outflows, but they're less spatially resolved. So it's more difficult to study the outflows in detail. So we kind of look at the intermediate range, which is to look at nearby Seyfert galaxies. And so these are basically moderate luminosity, radio quiet AGN. Early studies from the ground revealed that there was definitely some sort of non-rotational motions going on. There were some hints in the spectra. However, this was really, we were able to do this in much greater detail with observations from the Hubble Space Telescope. So for a little context, here is NGC 4151 and 1068. These are two of the brightest, most well-studied Seyfert galaxies in the sky. I would confidently say that with all the people on this call, we probably have more than 100 cumulative years of career study on these two galaxies alone. And so if we take a spectrum of these, particularly the central region, we get these very rich spectral features. So we can identify these narrow forbidden emission lines. We have broad permitted lines from the broad line region. And all of these other emission lines are coming from a wide range of different ionized species, different elements. And so this gives us an immense amount of spectral information, but we don't necessarily have the spatial information for where each of these individual emission line regions is coming from, how it varies as a function of different components in the galaxy. And so if we return to a ground-based image of 4151, we can kind of make out the structure. We have the more yellowish bulge. We have this blue ring of bright star formation. But when we use Hubble, we can really zoom in and be able to kind of dissect the individual components of the galaxy in greater detail. We can separate out the emission. And so if we use a narrowband filter to isolate in particular the bright oxygen 3 emission line, we can see very clearly this hot, excited, narrow line region gas. And so I really enjoy this image because it gives a true kind of visual representation of what this gas looks like. Down in the center, we have our hidden AGN, our source of ionizing photons, and that's exciting this gas, lighting it up and causing it to glow in this bluish whitish hue. So this gives us an idea about the distribution and the structure of this material. The other half of our investigations are, of course, spectroscopy. And so if we had just simple galactic rotation and we look at the O3 doublet on the right, we might expect some red shifts and blue shifts for normal rotation. And that is what we see, but we also see the gas moving at much higher velocities. And so this is that kinematic signature, that velocity signature of the outflows, where we have gas moving at several hundred or even a few thousand kilometers per second. So to kind of link this all together, here's an animation that I like where we have down in the center our AGN, our source of ionizing photons that's propagating out into the galaxy, ionizing this gas, exciting it, and then driving it away from the supermassive black hole at a few hundred to a few thousand kilometers per second. So this is really the picture that I want you to keep in mind when we're thinking of these narrow line region outflows. So with this, we have a couple of open questions that we're interested in tackling. So the first is, how common are these outflows and what mechanisms actually drive them? In addition, where are they launched from and how far do they extend into their host galaxy? What's kind of their ultimate fate? And then what is their actual energetic impact? So how massive are these outflows? What are their outflow rates? And what's the evacuation timescale to remove this material from the inner regions of the galaxy? And along with that, we first have to ask, what's the most accurate ways to actually measure some of those properties? So right here up front, I'd like to highlight that there are many incredible researchers working in this hot area, as was mentioned. And so there are a variety of excellent studies out there tackling these and other questions. Some of the folks are in our call today. But of course, there's only so many hours in the day. So I'm going to focus specifically on the studies that we've been doing recently to try to tackle some of these questions. So first we had, how common are the outflows? And so this was work that was really led by Travis Fisher and Mike Crenshaw. And so first we look at this image of Markarian 573. And this is a very nice example of a nearby Seyfert 2 galaxy at about a distance of 70 megaparsecs. And we have a variety of data sets that we're using to study these objects. So first we have the Hubble Space Telescope Imaging Spectrograph, or STIS, and the slit for that is shown by this very narrow green set of lines. So this gives us very high spatial resolution spectroscopy of the narrow line region. We also do some follow-up observations using the Apache Point Observatory Dual Imaging Spectrograph, which has a much wider slit shown in red. And so this doesn't give us high spatial resolution, but we can probe very faint emission into the large extended regions of the galaxy. And so this helps us kind of piece out where outflow begins to transition back into just smooth galactic rotation. And finally, a favorite instrument of a lot of folks who are doing AGN research is the Gemini near-infrared field spectrograph. And the 3x3 field of view is shown there in blue. And of course, we really enjoy this instrument because we get a spectrum at each location within the field of view itself. So for this particular study, Travis basically gathered all of the HST STIS spectra for Seyferts with inside a redshift of 0.05, with the majority of those inside of about 100 megaparsecs. And so this corresponds to 53 Seyfert galaxies. And with the spatial resolution of HST, we can get down to scales ranging from 2 to 100 parsecs. So we can see the small scale inner regions of these objects. They then fit the strong O3 lines and basically looked at the gas velocities, the gas kinematics, and put them into different categories, either clear outflow signatures, somewhat more ambiguous or complex, or very compact. And what kind of came out of this is that in general, the maximum deep projected velocities of these outflows tend to be around 1,000 to 2,000 kilometers per second. And in addition, a substantial portion of them show this kind of clear biconical shape, which we saw in the animation. And so for these systems, it's kind of this model where we have the ionizing radiation shown in red intersecting the host galaxy disk shown in black here. And so it's basically lighting up that material in the host galaxy disk. And we've gotten more support from this using follow-up observations from Gemini NIFs. And so this is part of an ongoing program we have led by Mike Crenshaw, where we're obtaining Z-band observations for a large sample of AGN that already have K-band observations in the archives. And so here we're looking at 3 different velocity fields. On the left is the CO bandhead. So we're looking at the stellar gas kinematics, the stellar kinematics. And so we can see basically a nice red shift and blue shift on either side. And that's that signature of just kind of calm, orderly galactic rotation. Then in the center, we're looking at the sulfur 3 line, and this is kind of our near infrared proxy for O3. So it's tracing that hot narrow line region gas. And when we subtract off that velocity field, we see this very clear signature of red shifted and blue shifted outflow on either side of the nucleus. Finally, because we have the warm molecular lines in the same bandpass, we can then go ahead and compare the kinematics of the ionized and the warm molecular gas. And here what we kind of see is that material appears to be rotating into the ionization cone of the AGN. It begins to get heated up and excited, and then it's being driven out with the outflows as well. And so there's a lot of work to kind of piece together the multi-phase picture here. But overall, kind of this picture we're seeing is that these cases with a clear bicone outflow is likely a nice intersection of this ionizing radiation field with basically the host disk of the galaxy. So this gives us an overall feel that we're seeing outflows in a lot of these targets. In some cases, it's a very nice, clean, clear signature. In other cases, it's more ambiguous, but it's clear that the gas is being perturbed. And so the next piece of the puzzle to tackle is basically how is this gas being launched and where is it being launched from? And so this is work that's being led by Bina Mina along with Mike Crenshaw. And so the overall idea here is, well, let's just model the forces acting on the gas, such as the radiation pressure and gravity, and see what happens. So here on the right, we're looking at NGC 4051, and this is a nearby low luminosity AGN. And if we go ahead and look at the innermost regions with Hubble, we're able to isolate individual knots of emission in this kind of clear conical section where the other side is most likely hidden behind the host galaxy disk. And so what Bina has been doing in this study is isolating individual knots and looking at their gas kinematics. So she models the system, basically finds its orientation to figure out the true space velocities, and then uses GalFit in order to produce a model of the host galaxy gravitational potential. So using continuum imaging to basically figure out how, the inward pull of gravity as a function of distance out into the galaxy. Now, the interesting part of this is if we make an assumption that the gas started with 0 radial velocity, so it was just rotating around with the galaxy, we know the current velocity, and so we can basically use this to solve backwards for where these gas clouds were launched from. So the idea is if it starts at a 0 radial velocity, we have the force of radiation pushing outward, we have the gravitational potential pulling inward. These are both a function of radius, and then you can integrate and basically work backwards what the launch radii were. And so this is an example of that for NGC 4051. These individual dots here labeled are basically those knots of emission, and we can see they currently lie roughly 100 parsecs out to about a kiloparsec, and we can trace their launch radii back and see that they originate from within a parsec out to kind of several parsecs. Now, this is the lowest luminosity case. When we extend this to more targets, we start to see that you can launch gas from further and further out into the narrow line region. So here we're looking at the maximum launch radius versus the bolometric luminosity, the AGN. And these are using the observed data points. This is basically, we're looking at how far we see gas clouds that are being launched and have some sort of substantial radial velocity. And so this picture emerges that this is basically consistent with in situ radiative driving. So rather than having all the material originate at small radii, say very close to the torus, and then traveling large distances, the radiation is moving out, ionizing material at its local location, and then driving it from there. And so this has a couple of different consequences for the velocity profiles. So we often see these profiles where the velocities increase and then turn over and decrease. And so rather than interpreting this as material accelerating and then decelerating over a large distance, it's more so a function of how easily you can launch the gas based on the physical conditions. So at very small radii, the gas is more highly ionized. And so it's more difficult to launch that gas at high velocity. As you move outward, the conditions improve. And then at some point, there's a turnover where you start to lose ionizing flux. You start to encompass more host galaxy mass. And so you can't launch material at high of a velocity. And so this is still ongoing work. We're also looking into the implications for this as to any other driving mechanisms that might be at work here. But kind of the overall picture is that to first order, this definitely seems to be consistent with basically radiative acceleration at a variety of different radii. So with these two pieces, we now have a feel for how frequent these outflows are. We have some idea, we think, of where they're being launched from, where they're traveling to. The big question is, what is the energetic impact of these outflows? What is the full extent of their feedback? And so in order to answer this, we want to measure the gas masses within the outflows. We want to measure their kinetic energy, their momenta, and all of their respective time derivatives. So the mass outflow rate, the kinetic luminosity, and the momentum rate, which is going to tell us about where material is being evacuated from and where energy may be getting deposited. In order to do this, we're going to use cloudy models to determine the gas masses because we want to try to minimize the number of assumptions we have to make about the physical conditions in the gas. But this requires a very large spectral range in order to have a lot of emission lines to model. So we're going to focus on a few Seyferts with the best data. And so in particular, I've been focusing on these 6 galaxies here. So these 6 galaxies are drawn from the same sample of the 53 galaxies that were studied by Travis Fisher. And here we're looking at all Seyfert galaxies and 1 quasar. And these are all type 2 objects with no visible broadline region emission except for NGC 4151. So overall, this sample spans about a factor of 200 in luminosity, as well as some small range in black hole masses and Eddington ratios. So for each of these objects, we have an HST-03 image shown here in orange, as well as a STIS long slit spectrum, in this case showing the spectrum just from the nucleus. And so I kind of want to walk through this analysis process in just a little detail because this is what allows us to really tightly constrain the gas masses and the outflow rates. So first, we extract a spectrum at each location along the STIS slit, which is shown by this narrow rectangle in the lower image, and we fit the strong oxygen-3 emission lines. As you can see in the upper right, sometimes we have multiple kinematic components. In this case, we have one that's consistent with basically rotational velocities and another at the same location that's consistent with outflowing gas, moving at a few hundred to a few thousand kilometers per second. And when we do this at each location, we can then build up the velocity profile, which is shown in the upper left. And so we can see the velocity start near 0, increase to some maximum value, and then begin to turn over and then basically just transition back into galactic rotation. And so once deprojected, these maximum outflow velocities end up being about 1,500 kilometers per second. The next step in our process is to use those fits to O3 as a template to fit all of the other emission lines in the spectrum. And so we have things all the way from like neutral oxygen 1 up to iron 14. So we have a wide range of ionization here. So what we do is we use multi-component cloudy models. Basically, we allow for the gas to have multiple regions of different densities in order to fully account for the physical properties of the outflow. And so the key here is that the density is determined by basically the total ionizing flux, or the bolometric luminosity, divided by the distance that you're at in order to correspond to a flux, and the ionization parameter for that particular line. And so on the right here, we're looking at the ionization structure of the oxygen-3 emission line. So it's basically the strength of the line as a function of increasing ionization and increasing density. And what I want you to take away from this is that at very low ionization potentials, basically we have no visible emission from that line. As we increase the ionization, as we add more ionizing photons, we reach some maximum peak where the line is very strong. And then it begins to decrease at higher ionization as the line moves into other ionized species like O4, O5, O6, basically up into the X-ray regime. And so each emission line has its own particular structure. So for example, iron 14 sits at much higher ionization parameters, while oxygen 1 sits much lower. And so this is what's telling us that there's a wide range of densities present within the outflows. So basically we find that usually up to about 3 components is enough to match this. And the key is that because we know the distance of this material from the nucleus, that provides a full constraint. So if we pick an ionization parameter to match a line, the density is fixed. And so that reduces a large parameter space to basically a single line. And so this is the key that really lets us, we hope, provide very tight constraints on the ionized gas masses. So with this, we now have the mass within that HST STIS slit. Of course, there's a lot of emission outside of that. And so we scale the O3 flux in these concentric annuli from the image based on the flux in the slit in order to get the total mass at each radius. Of course, there's some assumptions there about azimuthal symmetry, which we've investigated, and I'd be more than happy to talk about that afterwards. So with this, we can basically convert all the O3 fluxes to gas masses and combine it with the gas velocities to get these key energetics, to get these mass outflow rates shown by the first equation and the energy flow rate, or the kinetic luminosity. And so without further ado, the results for this sample. Here are the logarithmic gas masses at each radius for each AGN with their luminosity shown in parentheses. And I want to point out that this is not an enclosed total that would just continue to rise. This is the mass at each point, basically within each radial bin for each AGN. And so we see that the mass at a given radius, as well as the total mass, basically continues to increase with AGN luminosity. And in general, we see that basically the mass continues to rise until we either start running out of ionizing photons, or there's an abrupt end, either due to the depth of the observations or the velocities of the gas basically transitioning back into rotation. And so these are all generally spiral galaxies, except for Markarian 3, which is an S0 that's being externally fueled by a companion galaxy. And so that might be one reason why we see this very sharp rise at small radii, because it has such a fresh supply of fuel. So if we combine these masses with the velocities, then we can get one of the most key parameters that everyone is interested in, which is the mass outflow rates. And so here we're looking at the mass outflow rate as a function of distance from the nucleus. And so again, we see this trend where basically the peak rate and the distance of the peak rate from the nucleus are roughly increasing with luminosity, but we see these strong radial variations that might otherwise be lost if we only had a single spatially integrated spectrum. And so we can see the peak outflow rates range from roughly 3 to about 12 solar masses per year, which is actually kind of surprising because these AGNs span a factor of 200 in luminosity, and yet the mass outflow rates are only spanning about a factor of 4. And so where we start to see that separate out is if we look at the energetics, or excuse me, if we look at the kinetic energy. And so in this case, we start to see some more differentiation in the total amount of kinetic energy in the outflow. And because these are not rates, these can be added up radially in order to get kind of the total kinetic energy of the outflow, whereas the outflow rates we can't add up because those are not a conserved quantity. They have to be sampled within a common radius. And so a lot of the scatter that we're seeing here is due to basically the differences in the peak velocities of these velocity profiles. If we look at the derivative of this, if we look at the kinetic luminosity or the energy flow rate, this is a value that's often used to basically understand whether these outflows might be delivering what we call effective feedbacks, if it's significantly impacting the host galaxy. And so kind of a common benchmark is for this value to reach roughly 0.5% to 5% of the AGN bolometric luminosity. And we're not quite seeing values that high here. In the most extreme cases, we're seeing something like 0.1%. So that's one piece of evidence that these may not be delivering extremely strong feedback to the host galaxy, but it's important to add the caveat that those models are also primarily applicable to higher luminosity targets, which are actively building their bulge and structure. The key here is that in this case, we now have a direct measurement of how rapidly material is being evacuated and how much energy is potentially being deposited and carried to larger radii. So if we take all of these together, we can look at how these properties, such as the total mass and the kinetic energy on the left, and their peak outflow rates on the right, scale as a function of the bolometric luminosity. Now, of course, there's only 6 points here, so we need a lot more data and a lot more investigations before we can fit any sort of slope to this and get a relationship. But it's giving us, these initial inclinations that we have a rough scaling between all of these properties. And most importantly, what we hope we're seeing here is that these multi-component models are letting us really tightly constrain these masses so we can do a more one-to-one comparison between objects without having large systematic uncertainties. So this is, at the moment, kind of what we think is the best that we're able to do. We're using all of the spectra, all of the imaging we have. We're trying to eliminate as many assumptions as we possibly can about the properties of the gas. But this requires an immense amount of spectra, a lot of modeling time. And so the question is, can we simplify this process? These models are giving us, what we think are good results, but we need a very large spectral range. And that only exists for a very small number of AGN at the same spatial resolution that we already require. So if we want to simplify this process, the first thought is, okay, well, the outflow velocities can be determined from a single emission line. We can measure the gas kinematics, and we can measure the luminosity of that gas from a single emission line. And so then the question is, okay, well, how might we go about calculating the masses? And so for this, we've been investigating two kind of different avenues, and this is a part of our ongoing investigation. So the first is single component models. So rather than using this multiple range of densities and all these different properties, let's just do a single component model, assume it's optically thick, and just run that and see what happens. And the second portion is to use what is most commonly used in the literature, which is the recombination equation. So in the case of photoionization, we have the luminosity of a line, and we have a model predicted flux that gives us the area of all emitting clouds. And then we have the model predicted column density, which gives us the total number of particles. And so that gives us the mass of the gas in that particular instance. In the case of the recombination relation, we basically are photon counting. So we're saying for the amount of light that we see at a given density, that is related to the mass by a constant. It's just giving us the mass per unit luminosity. And so that's assuming that the gas is uniform and fully ionized. So the key question, regardless of which approach you want to go with, is what are the gas densities? And so this is something I've been really interested in as a part of our ongoing work. So here what I'm showing are our cloudy model densities for two of the targets. I've chosen these because it's one of the most nearby lowest luminosity targets for NGC 4151 and our higher luminosity, more distant target for Markarian 78. And so what you're looking at are the different densities for our different components. So we have our high ionization in red, and that's what's matching lines like iron 10 and iron 14 and neon 5. And then we have a medium ionization component in green. That's what's matching things like O3. And then we have a low ionization, which is matching things like oxygen 1 and sulfur 2. And kind of the first key point here is that these span roughly 6 orders of magnitude between different components and as a function of radius. So now we say, okay, we want to go ahead and do this in more simplified form. So what density do we choose, right? There's a variety of densities. So we wanted to try to test as many different models as we could. So the first is if you have very little spectral coverage, especially if your target's less well resolved, you may have no real constraint on the density. And so the first approximation is to just choose a constant value. And so common values are 10 to the 2, 10 to the 3, and 10 to the 4, which are shown by these black dotted lines. So we investigated those. In addition, a second approach is to use density sensitive emission lines to basically get a constraint on the density of the gas. And the most common is often sulfur 2. And so shown here in gray are the densities that we get from the sulfur 2 emission line ratio, which is sensitive between roughly densities of 10 to the 2 to 10 to the 4. And finally, the third kind of profile that we looked at is a 1/r² profile. And at first thought, you might say, well, how does that come about? Why is that physically motivated? So you might notice that the medium ionization component in green basically follows this 1/r² profile. And so if you are looking at the O3 to H beta ratio across your narrow line region, if that's roughly constant, that tells you that the ionization parameter, the ionization state, is roughly constant. And in order to have both of those drop at 10 to the minus 2, the density also must decrease as 10 to the minus 2, or 1/r². So basically, we're going to look at this 1/r² profile as well as some deviations from that, basically a little steeper and a little shallower based on the O3 to H beta ratio. So there's a lot of information in this plot. I know I put a lot out there, but again, basically the key points is that we're going to look at photoionization models, single component and recombination using constant densities from sulfur 2, and basically these kind of clean monotonic profiles. So if we look at these results, first using the recombination relation, just assuming constant densities. Now our original cloudy model results are shown in black. For NGC 4151, it's kind of right at the bottom there. I apologize. I'll plot this in log next time. And so we can see the cloudy model results. And what we notice for all of the targets is that the common value of 100 for the density basically overestimates the mass in all cases because it's underestimating the density. And so this is most significant for the lower luminosity nearby targets, where we see, for example, in 4151, it's over predicting by about a factor of 60, whereas for the higher luminosity, more extended targets, it's over predicting by a smaller factor overall. But we're still missing those kind of radial variations. If we increase that to a value of about 10 to the 3, we obtain kind of a much better overall agreement, but we still see over and underestimations that exceed an order of magnitude. So this gets a little bit better if we use the sulfur 2 densities. In this cases, the sulfur 2 tends to match well at large radii, but it's still under predicting the density and over predicting the mass at small radii. And basically the reason for this is that the sulfur 2 doublet is only sensitive up to about 10 to the 4. At that point, it starts to become collisionally suppressed. And so those high densities basically aren't probed by that particular emission line. And so kind of one of the worrisome things here is that the mass outflow rates tend to often peak at small radii. So we want to make sure that we're measuring the density there as accurately as possible. And finally, the last piece I'll highlight is using single component photoionization models. I know there's a lot of curves here. What I want to draw your eye to is first, if we use just the 1/r² shown in green, it tends to work well for a lot of targets, but it also overestimates in some cases. And that's because we don't have a constraint on the column density of the gas. And so basically the models can just get optically thick. Now, if we go ahead and use the actual O3 to H beta ratio to basically get an exact value for the ionization parameter for that particular phase of the gas, we're able to get the results to agree within about factors of 2 to 5 in most cases. And so initially you might say, well, that makes sense. It's photoionization models, it's a similar approach, but it really is a big simplification. We're going from 3 different densities to 1. We're removing variations in the dust content of the gas between those components. We're only using a single direct SED. There's no filtering involved, things like that. So it's encouraging that we can potentially get somewhat matching results, even with these large simplifications for targets with less spectral coverage. So to kind of bring things home here, I know that's a lot of information. So as kind of an overall summary, the first is we've looked at kind of the presence of these outflows. And so we're seeing these velocity signatures in a large majority of nearby Seyfert galaxies. And when we go ahead and model those, we're seeing that it's consistent with this model of in situ radiative driving, where gas is being ionized, accelerated, and then driven out from its local location in the galaxy. When we go ahead and then model the masses and outflow rates of that, we're finding particular values that I'll highlight in a moment. But really what we're seeing is that there's this very large range in physical conditions within the outflows that we need to account for. And of course, we have not answered all of the questions, right? This is a very multi-phase, multi-scale problem. So we still have a lot of work to do to tackle the other phases. And there are many, many on the call who are experts in that area. So I welcome your discussion. So finally, to conclude, I think a few of our key takeaway points is that we see that the spatially resolved picture is really imperative for accurately modeling these outflows. If we only have a single integrated spectrum, it's very difficult to disentangle where material is being evacuated from and where energy may be getting deposited. Overall, we're finding outflow masses of about 10 to the 5 to 10 to the 7 solar masses, with outflow rates about 3 to 12 solar masses per year. And this is many times greater than the mass accretion rate onto the supermassive black hole. In addition, we're finding energetics with kinetic energies on the order of 10 to 54, 10 to the 56 ergs. They appear to be scaling with the bolometric luminosity. They don't quite reach those theoretical thresholds for effective feedback, but we still have a significant amount of material that's being heated and driven out. In addition, what these models have revealed to us is that the outflow density profiles are very far from constant. They can span roughly 6 orders of magnitude between different regions of ionization and as a function of distance from the nucleus. And while photoionization models are providing tight constraints on that, there is the potential to simplify the process if we're able to tolerate a little bit larger of an error budget, which may be necessary because we don't necessarily always have this large spectral coverage at high signal to noise for a lot of targets. And so kind of the next direction that we're moving here is to expand this to a larger sample that spans a larger range in bolometric luminosity, a larger range in host galaxy properties, using HST imaging that we recently obtained in cycle 28 to match archival STIS spectra. So this is a lot of information. If you can only take one point away from this entire presentation, I'd like it to be this one, which is that we cannot reasonably approximate the outflows as constant density. We see that they span a very large dynamic range in density, both just within ionization stratification of the outflow at one location, and particularly as a function of radius. So with that, I thank you very much all for making the time to join today, and I would be happy to field any questions.
Great, thank you so much, Mitchell. So let's thank Mitchell for an excellent, very clear talk. So we'll take questions. So I think Giacomo's hand was first, and then Matt, I see.
thanks. Yeah, maybe Matt raised the hand 1 second before. Yeah.
Oh, okay.
We were almost the same time. Okay, I can quickly ask a couple of questions. So first, I want to congratulate Mitchell with your talk. It was great, and I especially appreciated the part on the density, which you also wanted to highlight at the end. So I really like the resolved profiles of the density. And so since the density is usually the bottleneck for the outflow properties estimation, it seems it's even more complicated than we thought up to now. And so, but I really liked that you find when you go to higher distances from the nucleus, so lower densities, if I recall from your slides, something like lower than 100 particles per cubic centimeter, right? Yeah, and that's reassuring because, yeah, more or less, yeah, even in Mercurian 7A, 7-8, yeah, you go lower. Because in some objects, yeah, I also find really high densities in the center, like in this case, and then really low densities when you go away. I mean, using the sulfur 2, yeah, anyway, besides this, I had another comment on the kinetic rate that you previously mentioned, and compared with the AGN bolometric luminosities, the ratio you find was about 0.1%, I think you said, right?
It was about the maximum, yeah.
Yeah. Yeah. I mean, from one point of view, I think we should always remember that besides the ionized phase, there are also the molecular and neutral atomic phase. So the ionized phase alone may not be consistent with the predictions, which are higher for the coupling efficiency predictions for models, but maybe by adding the other phases, it could. But again, if we forget for a second about the other phases and we only consider the ionized one as if it's the only one, it might also be that according to the direct radiation pressure driving mechanisms models that you cited, also these low values could be consistent with this kind of mechanisms instead of with the like energy or driven mechanisms that predict, the nuclear X-ray outflow, which then propagates with an expanding bubble. Because the radiation pressure mechanisms give a lower prediction on the kinetic coupling efficiency. So these outflows could be consistent with this kind of mechanism, as you were saying in your presentation as well. So this was just a comment, and I wanted to know what you think about it.
Yeah, those are fantastic comments. There's a lot there. So I'll touch on 2 points briefly. I think the first is we absolutely need to go after the multi-phase picture. We've heard some work, including in the seminar series, where the molecular outflows may carry 10 times the amount of mass of the ionized phase. And so if they're moving at comparable velocities, that could absolutely, have a very significant contribution to the evacuation rates and to the kinetic energy. And so we are very open to collaborating on potential, ALMA observations, things like that. In addition, you make an important point about the more highly ionized phase, because if you look at these density profiles, the interesting thing that I didn't have the time to point out, most of the light is coming from the low ionization because it's the highest density. And so it's emitting very efficiently, but it contains only a very small amount of the mass. So for example, in one of these targets, the medium ionization, the high ionization, they contain more than 95% of the mass, but they're only emitting less than half the light. And so those density diagnostics are probing the most dense, efficiently emitting material, which has the least amount of mass. And so these very low density components emit very inefficiently. And so since we can see them, that's a good indication there's a lot of mass there. And so one thing that we're working on now, our collaborator had a paper accepted earlier today that is basically trying to use proxies to get a better handle on the X-ray gas. So using both Chandra and potentially using near infrared, very high ionization lines to try and extend this out to look at basically the footprint of the X-ray gas. And I think once we have a better handle on the kinematics and the masses of that, that will let us take a better look at kind of this energy conserving versus bubble scenario. So yes, thank you very much for pointing that out. Those are our key points.
Great. So we'll have Matt next, then Darshan, and then David.
So many very exciting, interesting results here. That brings many thoughts up. Since you have this graph right on there right now, just want to make a comment on this, and then I'll get to my main question. On this one, it's just a little bit frustrating, not anybody's fault, I guess, that our best density diagnostic measure, which is that sulfur-2 doublet ratio, refuses to really show us what we want to see. I wanted to, it's sort of just like a constant of 300 or 500 particles per cubic centimeter. I wanted to see that thing going down at least a little bit, maybe 1 over r squared, but I know, as you said, we're not really looking at all of the gas. Anyway, it's just a shame that it doesn't show us what we would like to measure, and it's hard to find other density diagnostics. It's just a bit of a bummer.
I will say that in some targets, we do see more of a decrease. In Markarian 573, we do see this kind of shallow power law drop off. So it definitely is still probing, some range in density, just not that full dynamic range. So for example, in 573, it goes from about 1,500 per centimeter cubed down to about 200 or 300, because we're kind of resolving this nice inner knot. But of course, yeah, the key is that this sulfur-2, which many are pointing out in recent papers, is mostly coming from this kind of partially ionized zone. And so, it's definitely probing a key component of the gas, just maybe not where most of the mass is in some cases.
Okay, can you go back to that very interesting slide, which has the dm/dt, the mass rates as a function of radius for the different galaxies? Yeah, just about there. Yeah. So, well, the mass rate is even more interesting, but okay. So my thought on this was, it's kind of intriguing that all of these 6 galaxies are kind of pushing out, I don't know, 5 solar masses a year or something like that. And the main difference is where they're pushing. So the low luminosity galaxies are struggling to just get some action in the inner few hundred parsecs. These, what you consider to be more luminous galaxies, are having a much bigger impact out to kiloparsec. I do want to warn you, by the way, that it sort of seems like your high luminosity, if they really are galaxies you picked out, you kind of have rather special, famous examples of outflows out there. But anyway, we need more data, but that's okay. So, but here's what I was thinking. I've always kind of figured that when you're looking at things that are out there at kiloparsecs, you're looking at a sort of a time averaged history of what the AGN's been doing for millions of years. And I always assumed that these AGN, they have similar black holes, and they eat and then they go on diets and whatever. So I would have figured that they would have different luminosities over the last thousands of years, the last 100,000 years. But no, I mean, your graph is saying it looks like those, what you call the high luminosity galaxies, apparently have been the bosses for a long time. They've always been, and 4151, 1068 never did anything for the last 100,000 years, because they didn't manage to push anything more than a few hundred parsecs. Or maybe you're not saying that. I don't know.
Well,
but
no, so you raise a very important point, and I'm glad you bring this up, because this often comes up, is the time average of the luminosity, right? Of course, these targets are very 4151 and 1068. There are those on the call that are better qualified to answer than me, but they do vary, certainly on short time scales, on moderate length time scales. But the key is that as long as it is roughly constant about a value on the light crossing time of the narrow line region down to the spatial scales that we're modeling, so say tens of parsecs to kiloparsecs, then we can go ahead and do this process across the narrow line region. Now, that said, we can also use this as a tool to determine the long-term luminosity variation. And the reason I say that is when we do the modeling process, if you look at this one equation here, it all goes into the luminosity of the AGN. And so if you are using, if you're using the O3 line, for example, it peaks around an ionization parameter of 10 to the minus 2. You have the distance, you have the current luminosity. If you use that for your densities and say out at a couple kiloparsecs, you cannot match those line ratios, that can be a good indication that the luminosity was higher or lower in the past. because you need to basically, you cannot match the line ratios at the luminosity that you see now. I think a famous example of that is the teacup. And there's a couple papers on that where basically you have this, ionized structure that's well out and indicates that the luminosity had to be a factor of 100 higher in the past. That said, I will not claim that, we could probe factors of 2 or 3, 4, something like that. But I'd say, if it changed by an order of magnitude on, thousands of year time scales, the light crossing time, we'd be able to potentially pick that up. So maybe we just got lucky with these few. We definitely have many more to model. So I actually do hope we find one where that's the case, because it would be an interesting proof of concept.
Great. Darshan and David and Claire, and looks like Rich and Mike have some comments in the chat.
Yeah. Hi, Michelle. Very nice talk. Thanks a lot. So I have two main questions, but I think I'll just focus on the one here. When you go back to your density profiles, I have to admit that I was a bit surprised to see that it's quite smooth. So they really go down like in some sort of a profile. So you'll be able to do some sort of a fit to see how this profile would extend even further. My question is that, is this the density of all the gas that is in the galaxy, or do you make an attempt to disentangle between what is outflowing and what is not? Because what we are interested in is only the light from the gas which is actually being launched from the accretion disk, or whichever radius that you can think about. So yeah, that's what I was wondering, that the comparison that you make here, are you comparing, say, the outflowing gas with an outflowing gas density, or are you just taking everything in this one bag?
No, so that's one of the key reasons that we want that HST STIS spectra, so we can dissect at each location the multiple kinematic components. So for a lot of these, there's kind of a clear trend of outflow and then transitions back into rotation. For example, Markarian 34, we're able to trace outflow and rotational components at all radii. And so for that, we isolate specifically the luminosity of the outflowing component. We calculate the gas mass for all of it, but then we separate out just the portion that's outflowing. So for example, in that target, it varies between roughly 10 and 100% of the mass outflowing at any given radius, and roughly a little bit under half overall. So this is probing all of the, I'd say, only outflowing gas. And to touch on your other point about kind of smooth profiles here, it's kind of a full circle of nature, in the sense that we are able to trace these medium ionization components that trace the O3 gas only where the conditions are right for O3 to emit, right? So if the gas was higher or lower density, it might emit in O2 or O7, for example. So then it might not follow this same profile for that specific component. So it's somewhat a function of following those specific ionization states of the gas. But I think, overall the key that we're interested in is seeing that range of densities at that one location. Looking at Markarian 78, even at one location within some given gas region, we have 2-3 orders of magnitude of variation. Excellent point, though.
Yeah, sure, thanks.
Great. So David?
Rich, amazing stuff as usual. Can I ask you a little bit about just so the mental picture of what we should have for the outflows? You mentioned radiative driving. Is when you model this, are you exchanging deriving momentum from the radiation primarily through the process of ionization? Do you include things like dust-driven driving, for example, and how does that change measures of the dynamics? And then sort of a follow-up question is relating to, you talked about Bina's work, where you can sort of trace back the path of these clouds, but the eventual point you want to make was that that's not a reasonable picture, that most of the kinematic structure we're seeing is in situ, and those clouds are not traveled particularly far. It's just that they're all accelerated by this particular phase, in which case, should we consider things like the filtering of radiation, so that the radiation field that is seen at small scales is not quite the radiation field that's seen in gas at larger scales, And so how does that affect things like calculating the cloudy models, the amount of momentum that you're putting into the gas on various scales? So a lot of things I mentioned here, but hopefully you can give me some viewpoints on what you think is the best way to think about this.
These are great points. So initially we started with the higher luminosity targets, and we had this picture kind of very clearly where gas is being driven at many radii out to hundreds of parsec scales. And so it's only as we started to go to the lower luminosities that we started to see those launch radii really shrinking. So for example, in 573, most of the clouds have only moved 10 parsecs, maybe, less than 100 in almost all the cases. Whereas in 4051, it looks like some of them have moved, nearly a kiloparsec, which is, a very substantial distance. So I think there's a careful balance there between, AGN luminosity, host galaxy mass, and those properties, because particularly for systems with a very shallow potential, there's, you can move things a lot more quickly. So I guess I would say that for particularly the higher luminosity range, it looks like we have this fairly consistent picture of radiative driving at a lot of radii, but we still need to probe that bigger range in luminosity and host galaxy mass in order to really get at that. As to the second part about the radiation field, in some of these cases, we do take into account filtering. And so what I mean is in different components, we use a slightly different SED. So for example, at very small radii, we see the sulfur-2 emission line. Now, based on what we see here, that shouldn't be, right? Because the densities are so high, it should be completely collisionally de-excited. And so either that gas is very high out of the plane and it only looks close to the nucleus in projection, or what we think is more likely is that that gas is seeing a filtered continuum. So some of the radiation was absorbed at smaller radii, and then that absorbed continuum, which basically lowers the ionizing flux, lowers the effective luminosity, is what's exciting that gas. And so that's definitely important in Markarian 573, Markarian 573. And so that's something we account for in some of these targets. You had one more point, but I think that's all I have off the top of my head.
Yeah, it was about dust, but let's
yes.
Let's pass it on.
Well, I'll throw this up here briefly. I didn't want to include the full thing because I didn't want to have to explain it all. But basically, this is the full equation for the radiative driving. And basically, you have your radiation term and then your gravitational term. And so the way to look at this is the radiation pressure is based on the luminosity, and then of course divided by 1/r² flux. And where the dust comes in is in this force multiplier. And so for fully ionized gas, it's just Thomson scattering. And this force multiplier tells us how many times more efficient the gas is at absorbing that momentum. And so particularly in the narrowline region, like in the O3 gas, that value can get very high. It can be between 500 and 3,000 as compared to X-ray gas, which might be 1 to 10. And so basically, it's looking like, okay, as long as you have the conditions right for that O3 gas, you can get this great boost in absorbing the ionizing radiation. And then at each distance, you're subtracting off the enclosed host galaxy mass, which of course is increasing as you move out. So that's kind of the more in-depth picture on that piece, if that helps. But yeah, so basically the dust goes into the force multiplier effectively. Yeah.
Great. So Mitchell, you have a lot of questions. So we're going to do Claire and William, and then Jeffrey can put a link to the Discord server for continuing questions and discussion.
I was gonna say I don't want to rush anyone. Keep asking questions as long as you like, and then we can head over to the Discord when everyone's done.
Yeah, we're going to take Claire and William's question and then thank Mitchell. So Claire, do you want to go ahead?
Thanks, that was a great talk. As you mentioned, in cases where there are molecular ALMA data, the mass outflow rates and mass loading, it can be much higher in molecular gas. And so I wondered if for any of your handful of galaxies that you studied really carefully, are there ALMA profiles that you can compare with?
So unfortunately, there are not for many of them. Some of them are outside the DEC range. For 573, we do have a lower spatial resolution observation. So we know the total mass of the molecular gas within the radii of the ionized outflows, but we don't yet have the resolved profile. So I think there are definitely ALMA observations of at least 2 of these, but I would definitely be interested to discuss that in more detail.
Great. William, do you want to go? And then
I believe you're still muted, William.
uh-oh, his audio might not be working. So if he can't get that figured out, then we'll have William ask his question in the Discord link. Okay, he's gonna figure it out in the Discord. Okay, so thank you so much, Mitchell, and thank you everyone for joining. So let's give Mitchell a round of applause again for an excellent talk.
Thank you so much for making time to join, everyone. I really appreciate it.
Yeah, thank you so much. And Jeffrey has put a link in the chat for the Discord, so please join for continued discussion and potential collaborations. So thank you, everyone. Thanks.
Thank you very much. Have a great rest of your day.